strings. I mean, what does a grammar do? Right, you start with a starting symbol, usually capital S. Remember, it's revision from chapter 2. Okay, so you start with a start symbol, and then you use your substitution rules in set big R. Remember, and you keep substituting or overwriting, if you like, the variables in your current string with the right hand side of your substitution rules, and that right hand side typically will contain a string of variables and terminals, and you keep doing that. You keep substituting. Now it's a context-free grammar, right? So that means that on the left hand side of the rule there's only one variable, right? That's the definition of context-free, although I don't think Sipser ever really spelled that out. It seems such an obvious point. He misses things, basic things sometimes. Anyway, so you keep doing that until when? When do you stop this rule substitution process? Well, when your current string ends up being just a string of terminals. They're all terminals. Then you stop. And you say that that string of terminals has been derived by the grammar. Okay? And then all the possible strings that the grammar can derive, that's said to be the language of the grammar. The grammar generates that language. Okay? Alright, so thinking along these lines, let's say this particular grammar, G, that we're putting into our algorithm. Imagine this algorithm now exists. So we put in grammar G, whatever it is, context-free grammar, of course. You put that grammar G into the algorithm, and that algorithm then will test whether that grammar G generates 0 strings. Okay. Now, how can it be that a grammar does not generate a string? It generates 0 strings. What sort of circumstances would have to happen for a grammar to not generate any string at all? Well, so you start with your start symbol, and you just never get. Now, given the rules, now it'll depend on the rules, of course. But given the finite number of rules that you have, the rewrite rules or the substitution rules, as Sipser calls them, it may be, given the set of rules that you have, it may be that you just never end up with a current string that you keep substituting into. You may end up with a current string that is not a string of terminals, right? There'll always be variables in it, I guess. Yeah, have to be, right? So there are always variables in it. So it could be that you have a grammar, given the rules that you have, that you just never end up with a string that contains only terminals, right? So let's concentrate on that idea. So how would you go about testing that? Well, and here's the core idea. Okay. Work bottom up. Put markers on all the terminals, all the terminal symbols. You can mark them. So that means you'd have to double the number of symbols you're using in your set of terminals. If you had a terminal symbol TI, let's say, you need another symbol, dotted TI, so, with the dot over the ith symbol, T, TI, dotted. All right, so start with that, and then go through all your rules systematically, and see if you have some variables where all the symbols on the right hand side of a rule with that variable on the left hand side, see if they're all dotted, all the symbols on the right hand side of the rule, and if they're all dotted, and that means well, we would say we're starting with just terminals dotted, and so and if all the terminals are dotted, so if the right hand side is just one or more, a sequence of one or more terminals dotted, which are now dotted, then the left hand side symbol, has to be a symbol, would become dotted. Okay, so after a while you're getting not only your terminals dotted, but your variables also increasingly would get dotted. Okay, so you keep doing this, you keep looping through this idea, and so more and more variables will get dotted until you reach a stage where there are just no more variables you can dot, given the rules. So you're limited by what your rules allow you to do in terms of all this dotting. And then here's the punchline. So you've dotted as many variables as you can. You just can't dot any more because the rules just aren't there to allow you to dot everything, let's say. So some of the variables, all of the terminals are dotted, and some of the variables are dotted, let's assume. And let's assume also that some of the variables are not dotted. Now the critical thing, of course, is what happens if your start symbol, your start variable, usually capital S, what if it is not dotted? Aha. Okay. Well, if you think about it, that's the essence of the proof. Quite a bit between the lines here. But if your starting symbol S is not dotted, then you cannot, and here's the punchline, you cannot generate a string of terminals. Right? Now think about that. This is a bit between the lines. And as usual, Sipser just throws it at you, assuming you have sufficient intelligence to see that that's absolutely obvious. Okay? Well, it may not be absolutely obvious, but with a little bit of thought, you can probably see why that's true. If you can't, we'll give it some thought. Okay? Now, so if you're substituting away, and eventually, we'll argue the other way. Imagine eventually you do get your starting symbol, capital S, dotted, right? And if it's dotted, then whatever's on the substitution rule that has that starting symbol S on the left-hand side, that means all the symbols on its right-hand side are dotted. Okay? And then you look at all the other, and say you look on that right-hand side, and it'll have, let's say it'll have some variables, but they're dotted. Those variables are dotted. And that in turn means that if you look at the rules that have as their left-hand side the symbol we've just been talking about, then that symbol's right-hand symbols also dotted, and so on. So sort of recursively you go down, 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 until eventually you've just, on the right-hand side, you've just got terminals, but they're dotted from the beginning. Okay? So in other words, you can, if your starting symbol is dotted, then you can derive a string that consists totally of terminals. Right? Well, it's about as clear as I can say it for the moment anyway. I'll move on from there, but I hope you see that essential point. Now, that's that's what I've been saying, and well into the second session, I think. Okay, so the essence of the proof then is, if you can once you loop through this process of dotting all your dotting the variables whose right hand side, all the symbols in the right hand side of the rules of a variable. Put it this way. You look at all your variables each time. You sort of loop through this, looking through all the variables, and you're looking for non-dotted variables. And you find one, let's say, and then you look at the right-hand side of the rule that has that variable on its left-hand side. Just one variable, always. It's a context-free grammar. And then you look at the symbols on the right-hand side, and if all of them are dotted, then you dot that left-hand variable. Okay, you dot it. And you just loop through this until eventually there's no more variables that you can dot, and then you come out of the loop, and then you test to see whether the start variable, big S, is dotted. If it is dotted, then a string can be generated by that grammar, in which case the language of that grammar is not the empty string. So your Turing machine, which is testing all this, deciding all this, would give the result, the decision, it decides, reject. Okay? It is not the empty string. It's not the empty set. And if the start variable, big S, if it is not dotted, then you cannot generate a string from the start symbol. Okay? Because if it's not dotted, that means somewhere on the right hand side there will be some variable that is not dotted. Okay? And so on. You can, and recursively you go all the way down to the terminal symbols, and that means you cannot generate from the start symbol. You cannot generate a string that consists all of terminals. Can't be done. That's sort of saying it a slightly different way. Maybe that'll make things a little clearer why that's the case. Okay. So if your start symbol is not dotted, then it's impossible to generate any string consisting of terminals. So that means that grammar generates 0 strings. In other words, the set of strings that it does generate is empty. And that's what you want. That means the algorithm has found that that grammar, context-free grammar, CFG, labeled big G, it generates 0 strings, okay? The empty set. So the Turing machine, the algorithm, gives a decision and says accept that, in other words, this grammar G generates the empty set, generates no strings. Okay? Well, I've done well into the second session, so probably next session will be quite quick.